Welcome to the deep dive. Today, we're really digging into something called Gimbal Lock. It sounds mechanical, and it started that way, but it's actually this kind of elegant mathematical problem, too. It affected spacecraft, early 3D graphics, basically anywhere you have complex rotation.
Exactly. At its core, gimbal lock is, well, it's when you lose one way to rotate something. 1 degree of freedom, gone. It happens when two of your rotation axes line up perfectly. They become collinear.
Right, like two rings in a gyroscope lining up.
Yeah, that's the mechanical origin. But the real issue, especially now, is mathematical. It's baked into how we often describe rotation using Euler angles, roll, pitch, and yaw. That convention has this built-in failure point.
And it's not a small failure point, is it? I mean, the consequences are pretty significant. If that middle rotation, the pitch, hits 90 degrees, boom, your 3D system kind of flattens into 2D.
It's a singularity. And you mentioned spacecraft, think Apollo. Their guidance computer, it had calculations that involved dividing by the cosine of that pitch angle.
So cosine of 90 degrees is 0, division by 0 territory. That's bad.
Very bad, especially when you're trying to get to the moon. The inertial measurement unit, the IMU, on Apollo used a 3-gimbal setup. It was inherently vulnerable.
I remember reading that Michael Collins on Apollo 11 actually asked for a 4th gimbal for Christmas. He knew the risk.
He absolutely did. They had workarounds, of course, procedural things. The computer would flag a warning at, I think, 70 degrees pitch.
Okay.
And then if it got really close, like 85 degrees, the system would actually freeze the IMU to prevent hitting that singularity. Just stop it.
Wow. Just freeze it in place.
Yeah. And we still see this exact same problem today, just maybe less dramatically named. In robotics, they often call it the wrist singularity or sometimes the wrist flip.
The wrist flip.
Yeah, on an industrial robot arm. If two of the wrist joints line up, the control system loses track of one direction. And its attempt to compensate can be, well, pretty violent. It might suddenly command the wrist to spin 180 degrees out of the blue, unpredictably.
That sounds dangerous. So why does this keep happening? Is it just bad design, or?
It's deeper than that. It's fundamentally topological. You can't perfectly map the way Euler angles work onto the actual space of all possible 3D rotation.
Okay, unpack that a bit. Topological.
Think of it like trying to perfectly flatten the peel of an orange onto a table without tearing it. You can't. The space of Euler angles is like a 3 torus, mathematically speaking.
Right.
While the space of rotations is different. It's called SO3. They don't match up perfectly.
So there have to be points where the mapping breaks down, like
Yeah.
Gimbal Lock.
Exactly. The mismatch guarantees these singularities. It's not just a glitch. It's inherent to using Euler angles that way.
Which naturally leads to, how do we fix it?
Right. The solution, the one used pretty much everywhere now for complex stuff, is quaternions. These were discovered way back by Sir William Rowan Hamilton. It's a number system, but with 4 dimensions.
4 dimensions. Okay, so how does adding a dimension help?
Instead of breaking rotation down into that sequence roll, then pitch, then yaw, which is where the dependency and failure comes from, a quaternion represents a rotation as a single operation. It's defined by an angle, theta, and a single arbitrary axis of rotation in 3D space.
So it's holistic. It doesn't rely on that specific order.
Precisely. It bypasses that whole hierarchical dependency chain. And mathematically, the space quaternions live in, the 3-sphere, does map correctly onto the space of rotations. It covers it properly. No singularities.
Okay, and this is why they're so good for animation and graphics.
Yes. That continuity is key. It allows for something called spherical linear interpolation, or SLIRP. SLIRP basically finds the shortest, smoothest rotational path between any 2 orientations. No weird flips or jumps, just smooth movement.
Right, which you definitely want in games or simulations. I heard id Software's Quake back in '96 was one of the big early adopters.
It was. That was part of the, quaternion revolution. They used quaternions for the core rotation logic. It's also just much more efficient for combining rotations.
More efficient? How so?
Well, combining 2 rotations using quaternions takes, I think, 16 multiplications.
Yeah.
Doing the same thing with standard 3x3 rotation matrices takes 27 multiplications. That's a big difference when you're doing it thousands of times a second.
Wow, okay. So faster, and it avoids Gimbal Lock. Seems like a clear winner.
It really is for the core computations. Though, interestingly, we often still convert back to Euler angles for user interfaces just because roll, pitch, yaw is more intuitive for humans to think about.
That makes sense. So we need 4 dimensions, mathematically, to properly handle 3-dimensional rotation without these pitfalls.
That's the essence of it.
Okay, so here's something for you, the listener, to think about, building on all this. Quaternions solve Gimbal Lock. They're efficient, they map correctly, but there's a quirk. Every single physical rotation in 3D space can actually be represented by two different unit quaternions, one called dollars and its exact negatives.
That's called a double cover. Two mathematical descriptions for one physical reality.
Right. So the question to ponder is, what are the practical implications, if any, of having that dual mathematical identity when you're building, say, a control system for a robot or a spacecraft that absolutely needs perfect, unambiguous stability? Something to mull over. We'll see you next time on The Deep Dive.